it is part 2 of section 16.2. In the first part, we introduced the line integrals with the arc length segment ds. Here we'll study line integrals with respect to coordinate variables x and y. Let's see the definition. Integral over c f of xy dx is the limit of Riemann sums. For a given partition, f of xi star, yi star is a function value in the ith subregion. Delta xi is change in x in the subregion. Of course, delta yi is the change in y in the ith subregion. This is definition. Once the curve is parameterized, then here x is x of t and y is y of t. So here the differentials dx and dy can be written in this form and use these to get this formula. Integral over c f of xy dx is integral a to b, f expressed as a function of t, and x prime t dt. For integral with respect to y, we are using y prime t rather than x prime t. This equation is a definition. Now this one is for calculation. By using these formulas, you can get the integrals. Okay, we have a remark. It happens frequently that line integral with respect to x and y occur together, as in this equation. Integral over c of function p dx plus integral over c another function q dy. In this case, we write this integral in this form. So we try to omit one integral, just use one of them. There's notation. Now we define a vector field. Capital F is P and Q, and R is the transformation parameterization, so it's xy, and representing the curve. Then dr must be dx dy, so that this is the dot product of f and dr. So we can write in this way. This is a line integral of a vector field capital F, and we'll consider it in detail in the last part of the section. Okay. This is the problem. Evaluate over c y squared dx plus x dy, where we have two curves, C1 and C2. One is a line segment from this to that point, and another one is parabola, and from the same end, same initial and terminal points. First, let's try to visualize the curves. Okay. Now we have x and y coordinates. So there is x direction, and that is now y. And 0, 2 is the terminal point, and initial point is x is minus 5, y is minus 3. Okay. That is now minus 5 and y is minus 3. So let's see here now, minus 3. So here, C1 is straight line segment from here to there. So that is C1. Okay, C2 is along the curve, the parabola. Okay, that must be given in this way. Of course, that's the direction that is C2. Okay, so we'll try to get the line integral with these two different curves. Okay, let's focus on C1 first. And C1 is the line segment, so that can be written, that can be parameterized by using this formula. And t is moving from 0 to 1. This is a linear line, and once t is 0, then r0, that is beginning point, and once t is 1, then this portion will be 0, and r1, which is the terminal point. So we can write here r of t, the parameterization, is now 1 minus t beginning point, which is now minus 5 and minus 3, and end point t times end point is here 0 and 2. Right? Okay, for this one, okay, now we may write in this way. Okay, this is 1, so that minus 5 and minus 3, and this is, okay, minus t, so that we subtract from this one, so that t, and that is 5, and again 5. Okay, this point minus that one, that's exactly this one. Right? So we have here the parameterization, that is first component is minus 5 plus 5t, and second one is minus 3 plus 5t. Okay, that's the parameterization. So for the integral, the given integral with respect to now C1, okay, so we try to use some other notation here. Let's try to use this one. Integral over C1, that is, what is the integrand? Integrand is y squared dx and x dy. So y squared. So that is integral from 0 to 1. T is moving from 0 to 1. So y is this one. So minus 3 plus 5t squared. And x prime, which means that is 5, and dt, plus now x squared, y squared dx, and x dy. So x is here minus 5 plus 5t, and y prime is again 5, and dt. So we can put 5 outside, and the integral from 0 to 1, and that squared. So it is a minus 3 plus 5t squared, and then that is minus 5 plus 5t, and dt. You can simplify this one, and quite easily you can get the solution. Okay, so it's a 5 from 0 to 1, and for t squared we have now 25 t squared, and from this one we have minus 30t and 5t, so that minus 25t, and for constant we have 9 minus 5, so that we have a 4 dt. From now on, it's quite easy to get, and if you try to get the final evaluation, then you will reach at minus 5 over 6. Okay. So we have line integral along C1. The answer is this one. How about now C2? Okay, C2, this parabola, the equation is given in this way. X is 4 minus y squared, so that if we choose y equal t, then x must be 4 minus t squared. Of course, y is moving from minus 3 to 2, so that here minus 3 and t upper bound is 2. Okay, this is the parameterization, and along C2, the line integral can be written as the t integration. T is moving from minus 3 to 2, and y squared dx, that is y squared is t squared, and x prime is minus 2t and dt. Okay. And the second portion is x, so that is now 4 minus t squared, and y prime, which is 1, and dt. Okay, for that one, we have integral minus 3 to 2 for t cubed. That's minus 2t cubed. Okay, we consider this one. From second one, there's minus t squared plus 4 and dt. Right? Okay. Once you evaluate this, then you can reach at the value, and 40 plus 5 over 6, I believe. Okay, let's see here the result. Okay, yeah. So once you evaluate by using the technique you learned earlier in calculus 2, you can get it quite easily. Here, the main point is that the line integral can be different even though the initial point and terminal points are the same. And if you are trying to get the line integral along with a different path, then the value can be different. Right? That's one example. Okay, orientation of curves. Once you try to get line integral with respect to x or y, and then the orientation is quite important, and so that we have to consider orientation. For example, a curve is parameterized from A to B. Then once it is called C, then you may parameterize the same curve but the opposite direction. Then we call the curve minus C. So once you try to get the line integral with the reverse orientation, then here we have negation of original integral. And in this case, once you are moving, okay, if you're moving this way, then again we consider that is x positive direction, then dx will be positive. No, for that one is positive. But once you are moving this way, then dx in Riemann sum, delta x is negative. X in change is negative. So that already this one is involving negative, so that you have to put here minus, so that these two terms are the same. Exactly the same way for y integral. You have to put here negative when you try to get reverse integration. Okay. With that, now once you consider arc length segment ds, then the integral, even though you do the reverse orientation, the value must be the same, because in this integral, your ds is just length. So either direction, length is the same, so that for the arc length integration, this reverse orientation of the curve doesn't affect the integral. Okay. Now let's see the reverse curve minus c1 we considered in this example. Okay, here the c1 is the line segment from minus 5 minus 3 to 0 2. For c1 we consider minus c1, which means from here to there. Okay. Then it can be parameterized in this way. Now this is the beginning point, and this is the terminal point. So here 1 minus t beginning point plus t the terminal point. So we have that parameterization. It looks a little bit different, right? So let's try to get the integral for this reverse curve. Okay, so here the integral minus c1, that is, and t is moving from 0 to 1, right? And y squared, there's y. This is a 25 t squared, and x prime, which is minus 5, and dt, plus what is x? X is minus 5t plus 2. This, oops, okay. I'm sorry for that one. Okay, now I used the wrong one from here. Okay, y squared, that's y, okay? That is a minus 5t plus 2 and squared, and x prime, that's minus 5, and dt, plus x is minus 5t, that one, okay, which is x is this one, and then y prime, which is now minus 5, and dt. Okay, so we can put minus 5 outside the integral, and from 0 to 1. Now this one makes here 25 t squared, and that is now 20 minus 20t and minus 5t, so minus 25t and plus 4 and dt. Okay, let's go back to the answer here. This one is along with 5 and this term, integral over 0 to 1. So we can get this value along with this 5. Now, this integral is exactly the same, except here we have negation, right? So that eventually we have to get negative of earlier solution 5/6, which must be 5/6. So that's exactly the negation of the integral over C1, right? Okay, so once you consider reverse curve, then for such integral with respect to coordinate variables, the solution answer must be negation of the original one. Now, the line integrals can be easily applied for curve in space, three-dimensional space. Suppose that C is a smooth space curve given by that representation transformation. Then the line integral of f along C is defined in a similar manner as earlier. So we have here integral over C, f of xyz, and arc length segment as here limit of Riemann sum for a given partition. This is a function value in the ith subregion, and that is the arc length in the subregion. Okay. Now ds, so that in ds as r prime magnitude dt, we already earlier know that for parameterized curve, this integral can be obtained by using this formula. So practically, we reach this formula in detail. Okay. Now, once we choose the function is always the 1, then that becomes the arc length. And now again, same way, and in coordinate variables x, y, z, we may consider an integral occurring together, x directional integration, y directional. Of course, the integration is along the curve. However, we consider only change in x direction, change in y direction, change in z direction. Along with that variables, we can get line integrals, and these line integrals occur together. Then we may write in this way. Okay, exactly the same way as for functions of two variables. Okay. Now, let's try to solve this problem. Evaluate the line integral along C, y sine z ds, where C is the circular helix given by the representation r of t, cosine t, sine t, and t. T is moving from 0 to 2 pi. Let's try to visualize the helix. Okay, this is xyz coordinates x, that is y, and this is z. If we ignore this third part and assume it's 0, then this 2 will make a circle on the plane, but t is moving from 0 to 2 pi. So when it is turning around one circulation, now z value is increasing from 0 to 2 pi linearly, so that we start from here, and that is 1, and then circulating, and now is increasing like that. So it is turning around and coming up. So the height here is now 2 pi. if we measure the height here, then there must be 2 pi, right? Okay, that's helix. And once you try to get t larger, then it is turning around, coming up in this way. So it is called helix, okay? Now, so it's parameterized in this way. So when we try to get the integral, first we have to consider ds. Okay, ds is same as r prime length dt. What is r prime? R prime is derivative of this one. So minus sine t, and sine t becomes cosine t, and t becomes 1. Okay, and dt. Now, squared, summation must be 1, squared is 1, so that this length must be square root of 1 plus 1 and dt. So we reach at square root of 2 and dt. Okay, it's a constant. So the given integral is the same as from 0 to 2 pi. Okay, t is moving from 0 to 2 pi, and y is sine t, and now sine z is t. Okay, so we have one more sine t, and ds is the same as square root of 2 dt, right? Okay, that is a square root of 2 coming out of the integral, and 0 to 2 pi, and sine squared of t. You may try to use the formula. Sine squared of t is half of 1 minus cosine 2t, and cosine squared of t is half of 1 plus cosine 2t. So that is half of sine squared of t, 1 minus cosine 2t, and dt. Right? T is moving from 0 to 2 pi, then 2t is moving from 0 to 4 pi. That means that this part makes 2 full cycles in cosine graph. Once you make a full cycle, then halfly positive and halfly negative. The positive area, negative area are the same, and they are negation to each other, so that here this one will make no contribution. In fact, integration of that one must be 0. Okay, so we may ignore this portion. Then now only we have constant half times 2 pi, which must be pi, so that the final answer must be square root of 2 times pi. Okay. Okay. Let's go to another problem. Evaluate this integral where c is given by x is t squared, y is t cubed, and z is t squared. T is moving from 0 to 1. Okay, for this problem, quite easy. If we try to use the formula, then that is from, for example, now t is moving from 0 to 1, and z and x prime, and plus now x y prime plus and y z prime and dt. We have to put here dt, but we may write in this way, right? Okay. Now for this one, that's integral from 0 to 1, what is the t squared, and x prime is now 2t, and x is t squared, and y prime is 3 t squared, and plus y is t cubed, and z prime is 2t. Okay, so we have here from 0 to 1. Okay, highest order is power 4. We have here now, okay, power 4. So we have 5 of them. 5 times, okay, just a moment. Okay, this is not, okay. Power 4, this 3 and 2. Okay, so the 5 of t to the 4, and plus twice of t to the 3, and dt. So its antiderivative is now t to the 5 from the first one, and then here, is it correct? Okay, 5, okay. So there's t to the 5, and then there is half t to the 4, and from 0 to 1. So that we can reach at, this is 1.5, so that 3 over 2. So that's the final answer. Okay. Okay, we'll continue in the third part. Thank you.